Okay. Well, here's most of our data. We also had the 0, 1, 48, but that obviously fits because we kind of fudged it to make that happen. Okay? Just by picking the y-intercept as one of our points. Here are the rest of the points. How are we going to determine how good this model is? Well, what we're going to do is we're going to plug each of these times into the model and see how close it comes to what we observed. Okay? Now these were observations. I believe, well, the instruction, of course, was take 3 points on the curve that are not data points. A lot of people will use data points the first time they do it. As long as we get you out of that habit before we're done, that's okay. I don't remember if you did or not. Okay? I'm pretty sure you used the 0, 1, 48 for one of them. And that's okay. That's okay. It said to use that one. Okay. So what we're going to do is we're going to find our results using wrote that small, you might not be able to read it, but just using our function here. Well, if t is 26, t squared, everybody knows, is 576. Everybody knows that, right? 26. Okay. And 3/4 of 600 would be 450. 76, 3/4 of that is 18. Be 4. So I wanted to say, okay, yeah, that's good. And it's going to be 100th of that. So it's going to be like 4.32. And 2.3 times 26 is like 52 and 0.3, about 60, say. So that's 4 minus 60, which is negative 56 added to 148, gives you 90. Okay? Now, that's not the same as 93, and of course, that might be due to my approximate arithmetic, right? Can't rely on my arithmetic, but that came out pretty close. Okay, and maybe comes out closer, maybe not as close if you do the arithmetic. Matter of fact, I'm kind of thinking it comes out about 96.3, but okay. But no, I used too many approximations to be accurate. Okay. Now, 48 squared is about 2,300. And 2,400 times 175 would be 1,800. 2,300 would be about 1776. That would be about 17.7, say 18. And 2.3 times that would be 96. And 1,511. Now, what did I say the other one is? Working memory starting to fail me. And now I've forgotten what that one was. Maybe I better jot some things down. Okay, 2.3 times, yeah. I think I got 111. I think I got it. Minus that's 148 would be 148 minus 93, which would give me Yeah. Okay. Plug in 61, that's fairly easy. 60 would give me 3,600, which would come down to 700, so it'd be like 27. Remember 27 for me. And 2.3 times 60 would be 140. 23 minus 140 plus 108 is 31. Okay? That's very approximate because I use 60 instead of 61. Now you see these numbers are coming out close, right? And let's see, I'll do that real quick. 3/4 of 80 is 60. 60 times 80 is 4,800. And that's going to be like 4,700. It's going to be like 47 minus, I don't want to put a strain on it, 47. 2.3 times 80 would be 160, 174 times 78 would be 168. Would be like minus 20. We're getting like 17. Okay? And my mind seems to be at least halfway clear today, so those approximations might not be bad. Okay? Just straightforward numbers. 0.0075. So, now the point is, we compare these, right? And then I didn't leave myself room, but I'm going to leave myself room here. The discrepancy. 96 is 3 bigger than this, right? And actually I'm going to compare this one with this one. I'm going to say that our data is 3 less than our curve, than our function. Here our data is 2 less. Here our data is 2 greater. And here our data is 4 less. So these numbers are residuals. In other words, I'll use a little color coding. This number comes from this number and this number in the obvious way. This one's 3 lower than that one, right? Here's our model. We're comparing our data with our model. Our data is 3 below the curve. Okay? And here, if this is our curve, this is our data, then this point would be, well, this point would be 2 units lower than this point, right? I'm not talking about the curve you sketched, but I'm talking about the curve we get when we run through the whole process. Okay? And then the 31 and the 33, now this one's a little higher. And the 17 and the 13, now the data's a little lower than our curve. Okay? And the way this looks then, here's our y of t curve. And here are our data points. 2693 might be here, just a little low. Okay. 4853 would be over here a little more, and that's a little low. 6133, well, that's a little higher than our curve. We come out to 61, we got 33, and it's a little higher. Okay? Then we come out to 7813, and again, it's a little lower. Data point's a little lower. But they're all pretty close, and the curve makes sense in terms of a data point. And if you do, okay, remember that the original curve that you drew, this is not the original curve you drew, this is the curve that we got, okay? The curve that you drew should be pretty close to the curve that you got, okay? So that's another thing we want to check out. So this whole process where you start with your data points, white points here, okay? You draw what you think is the trend curve, you pick 3 points on that trend curve, and you do your quadratic model. You get your A, B, and C. And by a process that you understand pretty well at this point, this is what we get. We get this model, okay? That model will actually be the quadratic function that goes through the 3 points that you picked on the curve, okay? Any 3 points, we can do a quadratic model, as long as they all have different t-coordinates, okay? There will be a parabola that goes through any 3 points you want to pick, because we can always do this. We can then compare our model to our data to see if it makes sense. In this case, it looks like it makes pretty good sense, which means that by some accident or fate, I must have done the arithmetic reasonably well. Okay? Don't expect it to ever happen again. Right? So that's using your data, because everybody took different data. And using, of course, these equations, which were yours. They weren't mine, okay? Pretty good confirmation that these were good equations, right? So as expected, you've done good. And I'd said something good about you again, I've got to stop that. Okay. All right.